Jesse, we need to learn RLC circuits and differential equations. All right, Jesse, here's our problem. We have 20 amps, negative U, or U of negative T, 10 amps, times e to the negative 10t U of T amps. All right, so this is the problem we did on the quiz the other week. So we have a 20 ohm resistor, we have a 1 millifarad or millihenry inductor, and a 10 microfarad quiz problem that we did. This is going to be a little bit more of a complicated problem. We do have two storage components, energy storage components. So we're going to have a second order differential equation for this circuit. We also have a source. Now this source is a little bit complicated, and it's important to keep in mind all of the things that are next to it so that we can figure out when the source is being turned on, when it's off, when it's different values, etc. So this is going to be a little bit of an interesting problem to keep track of because there's a lot of things involved. So let's begin by establishing our t as less than 0. So let's draw this circuit, right? So before we make any changes, this is what our circuit was for a long time. We don't know how long. It's been so long. So U of negative T, as we went over it in the last video, you know, normally U is like that. Well, U of negative T would just be the opposite. So it's going to be 20 before you hit 0, and then it's going to be 0 after 0. So, and then vice versa, this 10e to the negative 10t U of T means that it's going to be 0 until you get to 0. So at less than 0, or t equals 0 minus, would probably be a better way to describe this. U of negative T is going to be on, which means that we're going to have 20 amps coming from this source. Okay? Now in this branch, we have our resistor, which is still 20 ohms. And in this branch, remember that it becomes IL stays, but this becomes a short. And then on this branch, we have, an open circuit with a VC voltage. So you can still have a voltage of a capacitor. You can still have a current of an inductor, but their impedance values are 0 here. So, or actually here the impedance would be infinity. But the point here is that you now have a circuit to work with to derive your VC of 0 minus and your IL of 0 minus, right? Which is going to be the two values that we need to get our VC of 0 plus and your IL of 0 plus. So this is a pretty simple circuit, right? We don't have to do Thevenin like we did on the last one. You only have one power source. So this is pretty simple. You're going to have 20 amps going around this loop. It's going to get dissipated by this 20 ohms. So it's going to be 20 amps times 20 ohms, and that's equal to 400 volts. That's going to be your VC, and then this 20 amps is coming around and it's going all the way through. So this 20 amps is equal to your IL. So your VC of 0 minus is 400 volts. Your IL of 0 minus is 20 amps. And this is going in the same direction as the IL pointed out in our problem, this IL over here. So no negative there. This is still, you know, positive side here, negative side here, so this is still positive 400 volts. Okay, moving on. So now we're going to do our T of 0 plus so that we can derive our differential equation, right? If we remember from the last video, your first step is to derive, your second step is to 0 input, and your third step is 0 state, right? So the first thing we want to do is derive this equation at time t is greater than 0. So t is equal to 0 plus. Now we're going to change our source, right? The source is not going to be 20 amps anymore. Now it's going to be this 10e to the negative 10t amps. So 10E negative 10T amps. Okay? And then this branch is going to remain unchanged at this point, 20 ohms. And now at time t equals 0 plus, your inductor, I can write this down, inductor acts like current source, and capacitor, a really badly written capacitor, acts like voltage source. Okay, so we're going to have voltage source, we're going to have a current source. That's really poorly done. And boom. So this is going to be your IL still. This is going to be your IC. And you know, we can mark on our previous thing if we want to. You know, this is your IC right here. So IC of 0 minus is equal to 0. And similarly, this is your plus minus VL, right? It's an impedance. So if we're acting like we're going into each one, this would be your VR. So if we're acting like we're going into it, your VL is 0 because it's not dropping any voltage there. So your VL of 0 minus is equal to 0. This is a VL of 0 minus is 0. Now those values don't carry over or anything. They don't really matter, but just for comparison's sake. So now we do have plus minus VL plus minus VR. Okay, and then this is plus minus VC, and so this is 400 volts. Okay, so now we need to analyze this circuit and figure out a differential equation based on the way the circuit is set up to derive the rest of our values, to derive our VC value. I'm going to move this down slightly, and we're going to derive it down here. So we are looking for VC in this problem. So we're looking for VC again, which means we're going to be looking for IC, because that is when you're trying to do the derivative. You know, differential equation is essentially a form of an integral. So when we're trying to find this, we need to use the derivative of it. So let's start with let's do some basic ideas. So this whole side is 400 volts, right? This branch is parallel to this branch, right? Which is parallel to this branch. So that means that everything here is 400 volts is this total branch, and this is 400 volts. So let's do a couple things. Because the other thing we should do is do some KCL at VA. Okay, and this VA is equal to VC. So let's just call this capital VC, so that it makes it easier for us to remember. So doing the KCL here, you have an I going here, you have an I going there, and you have an I going that way, right? So let's do that KCL. So you have a negative I source, right? This is your source, plus your IR, which let's keep in mind, by the way, your IR is equal to your IL because they're in the same branch, right? And then plus your IC is equal to 0. So, and then we've got this equation already. So let's keep both of these things in mind as we move forward. And then if we want to do some KVL here, you can do a loop here, a mesh loop, which brings you negative VL, negative VR, positive VC, right? It just did a loop around here, which this is IL. So theoretically, you could have some impedance here, and then IL times your VR, and then times your, or subtracting your VC, or adding, depending on which way you're going with your loop. So KVL, you're getting negative VL plus VR, I'm sorry, minus VR, plus VC is equal to 0, which means that your VC is equal to negative VL minus VR. Okay, so now I know we just did the KVL here, but our goal of doing this KVL is to figure out how to implement our currents into a way that we can we can derive our differential equation. So let's move back to this. And why don't we plug in here, VC is equal to our negative VL minus VR. Now let's substitute a couple things. So we know that our IL is equal to our IR, right? We also know that this right here is our general equation for KCL. So what we can do is we can plug in a couple values. You've got negative IS. Well, actually, let's solve this in terms of IL, because that's the one we don't know, right? We want everything in terms of IC. We don't have everything else. So if we have an IL, and your I source is fine, right? Because that's going to be for your particular solution. So we want everything in terms of IC. We know that this IR and IL are the same. So you have your IL is equal to your IS minus your IC, right? And so this is going to allow us to eliminate the L variable from our equation and put it in terms of C. So let's go back over to here. You have a VC is equal to negative VL is going to be what? IL is equal to 1 over L integral of VL, right? Or the other way to do this is DIL over dt times L is equal to VL, right? So what we can do with this is plug this value in. So this is going to be minus L times DIL over dt minus VR is what? Your VR is a current times a resistance, right? That's going to be the voltage. So this is going to be IL times R, right? All right. Well, this is great, except that we don't want any L's. So let's use this equation right here to solve for what we're actually looking for. VC is equal to negative L d over dt times IS minus IC minus IS minus IC times R. Okay. So now we're going to factor this down, bring this out a little bit, and we're going to put things to the proper sides. So we've got VC is equal to negative L DIS over dt plus DIC over dt minus IS plus IC. And actually these need to be both times R. ISR. Well, let's do RIS plus RIC. All of that is equal to, oops, we've already got an equal sign. Okay, so now let's do what we were talking about before, where we want, well, let's first off, let's plug in this equation. So our IC is equal to C dVC over dt, right? So I over C is equal to dVC over dt. So let's plug that in real quick, just so that we have everything in terms of IS and IC, and then we'll move on from there. So VC is equal to negative L DIS over dt plus DIC over dt. And actually, let's put this around. So let's d over dt times the derivative of IC would be this right here. So let's do the derivative of this part right here. So it's going to be C dV squared, d squared V over dt. Well, I put this dV, this was supposed to be of IC. But this was supposed to be of IC here, but that would translate to, we can skip this step. But so you just saw what I did. I did d over dt of IC, and we established that this is what IC is. So this would be C dV C over dt. And so what you're doing here really is you're taking the second derivative. So this is going to be C d squared V C over dt. So we can leave it like this, I guess, for right now, and I'll just put this down here. dis over dt is equal to vc. And then this is minus r times is plus r times c dvc over dt. Okay. Similarly, so let's bring this down, minus r times is, and then plus rc dvc over dt. Okay, so now our goal is to put everything on one side that is your c, and on the other side you want to put your is. So let's move this to the is side, and this to the is side, and this needs to move over to here. So you have c d squared vc over dt plus rc dvc over dt, and then you have vc, so minus your vc is equal to your r times is plus, plus L dis over dt. Oh, I'm looking at my notes. I made a slight error here somewhere. When I did, when I put this through, you see how you were supposed to distribute the negative L to both sides to the, oops, let's undo that. I was supposed to distribute this L to both sides. I did not put it here, so that needs to have an L there. This needs to have an L there. This needs to be LC, so that means that this needs to be LC. Sorry about that small error. That was just a distributing. So make sure you distribute to all of the currents, because I did distribute the R properly to both of the currents here. Okay, but now, so same thing as we were doing before. The only difference is this now has an LC. And then if you remember on the last one, you want your lowest order to have nothing next to it. You want it to have no coefficient. So we're going to divide this whole function by LC, because that's what's the coefficient of that. So that's going to give us d squared vc of t over dt plus, you're going to divide by c on both sides here, so it's going to be r over L, and then it's going to be dvc over dt, and then it's going to be minus 1 over LC vc, and then it's going to be is equal to r over LC is plus, this L is there, so it's just going to be 1 over c di, really badly written, dis over dt. Okay, and that should be our final differential equation. So this is the solution to our general differential equation that we are looking for. So all of that was set up, and now our goal is to solve this function using our 0 input and 0 states. So let's start back at the beginning. Whoops. Let's start back at the beginning, and let's write. So let's start focusing on the 0 input now. So we're going to have to draw the 0 input at time t is equal to 0 plus. So at t equals 0 plus, and this is for 0 input. I should probably put this down here so I don't forget that we're doing 0 input. So 0 input means that this is going to be 0 amps. That was our current source. We have the resistor here. We have the inductor pushing out 20 amps because it's still at 0 plus, right? 0 input still means that our values from before work, right? Our values are still charged. So we still have 400 volts, and our IL of 0 plus is still 20 amps. Those values still apply because our charged energy storage devices are still charged. So that will not change, which is our plus minus VC. This is 20 ohms. That's our 20 amps. Okay, so if this is 0 amps going through this branch right here, that means we have nothing going through that branch, right? So that means that we're going to have 1 voltage plus current source. All of this is going to go through this right here. And actually, it just means that we have this exact same function, but our IS is 0, right? Because this is our KCL, like this, right? IS, IR, which is equal to IL. This is our IC. So that means that our IS is going to be equal to 0. Oops, let's write this a little nicer. Which means we can rewrite our differential equation, probably plugging in some of our values along the way. That way it'll make our lives easier. And setting the whole thing equal to 0 since our IS is 0. D squared VC over dt plus 2 times 10 to the 4th. dVC over dt plus, what was our VC? Negative 1 over LC. It's actually going to be negative 10 to the 8th VC is equal to 0. Okay, so now we can solve this like a differential equation, which means that we can go S squared plus 2 times 10 to the 4th S minus 10 to the 8th is equal to 0. And we're going to need to find an S1 and an S2. You can use the quadratic formula. You can use really however you want to do it. I have a program in my calculator that just does the quadratic formula for me. So if I type in 2 times 10 to the 4th, and then 10 to the 8th, I get this one is equal to negative 10,000, and this one is equal to negative 10,000. So this is actually a critically damped system based on the roots that we found. The important thing to note about the critically damped system is normally we have the general solution, like when we do VC of t is equal to AE to the negative S, or I'm sorry, to the S1 t plus BE to the S2 t, right? That's typically how we'll solve this problem. In this circumstance, because our roots are the same value, we're actually going to have to add a t to this b function. So that's unique to the fact that when you have the same root, you have to have that in there. So this is going to be what our general solution to the problem is. And so for 0 input, I think we have what we need to at this point. Actually, I think we might have to solve for IC still, but let's plug in here first, right? So we know that our VC of 0 plus is equal to 400 volts, which is equal to AE S times 0 plus B times 0 E to the S2 times 0, which means that this whole thing is going to go to 0, which means that our A value is going to be 400. So VC 0 plus is equal to 400 e to the S1 t plus B t e to the S2 t. And reminder, you have your S1 and your S2 value already. I'm just plugging in the S1 and the S2 because it's easier to write. So now we have this value, but we don't have a way to find B because B goes to 0 here. So we're going to actually need to find the derivative of VC. Well, we can just write of T to start with, which, if we remember, is going to equal IC over C. And that's going to be the derivative of, here, let's rewrite this down here. Let's move this down. Oops, lost a piece. Let's move this down here, and let's paste this here so that we can keep a track of our derivatives. This is going to be A S1 e to the negative S1t plus And now let's do the derivative of this. So let's do the first, which is going to be t times the derivative of the second, which is going to be b times s2 e to the s2t, plus the second, which is e to the s2t times b, plus the derivative of the first, which the derivative of t is just going to be 1. So plus b e to the s2t. Okay, now our goal is to figure out what our IC is. So your IS is 0, which means that your IR is equal to your we can do this KCL if we would like. KCL. So you have negative, the IS is going in, so negative IS plus IR, which if we remember is equal to IL, plus IC is equal to 0, which means that IC is equal to negative IR. Okay? So, which would actually make sense, because if we followed this loop, right, we have 20 amps being created. So if we follow this loop going this way, right, then that means that our IC, which is pointing in this direction, is actually going to be negative 20. So IC is, so let's plug into this equation right here. So dVC over of T over dt is equal to IC over C, which is equal to negative 20 divided by 10 microfarads, which is equal to, let's see, we already have an A value, right? So this is going to be 400 times negative 10 to the fourth, and then at this is of 0. So this right here, this value is the E is going to go to 1, so times 1, and then this right here, sorry, it was this value that goes to 1, and then this right here is going to be times, so plus 0 times that whole thing, which means we're just going to make that 0 times bs2 e to the 0, and then plus you have a b function value here, and then you have an e value that's going to go to 1 as well, so b times 1, which is going to lead us to, that's going to lead us to negative 2 times 10 to the 6th is equal to 4, negative 4 times 10 to the 6th plus b, which means that b is going to be equal to, actually you're going to add that, so that's going to be 2 times 10 to the 6th. Cool. So now that's gonna, we can plug this stuff back in. So now our VC 0 input of T, which, apologies, I did this last problem too, where we need to be putting the 0 input here. 0 input, 0 input, 0 input, 0 input, 0 input. I'm sure there's a few that I missed, but VC of 0 input is equal to 400 E to the negative 10 to the 4th T, plus the B is 2 times 10 to the 6th times T, remember, don't forget that T, E to the negative 10 to the 4th T. Okay, so that's our 0 input equation. So now let's do the 0 state. So let's move on and do our 0 state. And we're going to redraw this for time t is equal to 0 plus. So at 0 state, remember the state, that means that the state of energy, really bad energy storing components is equal to 0. So we are going to act like we have, or we're going to keep our value of here, which is going to be 10e to the negative 10t. And we're going to still have our VR, but now this is going to become a current source that has 0 amps. And this is going to become a voltage source that has 0 volts. So let's do a little bit of circuit analysis right here. So now we have VC of 0 plus. Let's write VC of 0 state. 0 plus is equal to 0. We have IL of 0, let's write 0 state again, of 0 plus is equal to 0, right? And then we do have an R, well, this is still 20 ohms. Really bad. 20 ohms. And we basically have all of this current going down here, right? Because I mentioned if this is 0 volts, I think I mentioned it in the last video. If this is 0 volts, that means nothing's dropping, but you can still have a current. This is 0 amps, so no current is going down here. So this is going to act like a short circuit. All the voltage, or all the current is going to go down this way. So IC is actually equal to IS. And it is still going in the correct direction, so your IC is equal to your IS. And yeah, we already have this. So your IC of 0 plus, let's write 0 state again. 0 state at 0 plus is equal to 10e to the negative 10t. Which, by the way, since this is 0, right, that means that this is all going to go to 1. So 10 amps. Okay. So now that we figured out our general circuit for our 0 state, we're going to need to do our differential equation again. So this is going to be the same thing as before, over dt plus, I should have just brought this down. Let's copy this again. Let's see, let's copy this, paste, let's make it black. Okay, and we know that we do still have an IS over here, so now we have another differential equation, and this happened last time too. Because we have a particular solution here, we're going to have to do the homogeneous and the particular solutions. And so that we're not going to plug any of this in until we have both, right? So, okay, let's start with the homogeneous, which is going to be the same thing that we did before. 0 state homogeneous over dt, R over L, dVc 0 state homogeneous over dt, minus 1 over LC, VC 0 state homogeneous. And that's equal to equal to 0. And again, this 0 is different than before. This 0 is because we're doing it mathematically. So let us find the same thing we did before. We know that our S1 is equal to our S2. The equation didn't change, so we know that this is still negative 10 to the 4th. Okay, so our general solution is going to be the same. We're going to have VC of 0 state homogeneous of t is equal to AE negative 10 to the 4th t plus BT e to the negative 10 to the 4th t. Okay, so that one was nice and easy. Now we're going to do the particular. So the VC 0 state particular, and we're going to have a guess here again. So last time we guessed K because our voltage, or I should say our current source for that circuit was just a number, right? It didn't vary when it came to time. Well, this time we have 10e to the negative 10t. This right here is going to vary with time. So we're going to have some form of K times e to the negative 10t, right? Technically, you also need the derivative of this, and we talked about that last time with the derivative being a constant. Well, this time we're only going to have one value, because what's really happening here is that if this is your K1, you're going to add the derivative of this, which is going to be negative 10 times K1 e to the negative 10t. So technically, your total is going to be VC 0 state particular is equal to K2, which is just K1 times negative 10 plus your K1 e to the negative 10t, right? You're just combining the like terms here. So if we just call this a constant, it's going to end up being the same as just having 1K. So I'm going to erase all this, but this work is here so that you have everything. Actually, I'll just rewrite it down here. That way, if you're just copying stuff down, you have everything copied. But it's just going to be K e to the negative 10t. But that's why we only have 1K here. So, all right. And now I mentioned last time, too, you need to go down as many levels as you have orders of differential equation. So let's do dVC, 0 state particular, is going to be over dt. And this is going to be equal to negative 10K e to the negative 10t. Right? And then similarly, you're going to do d squared, VC 0 state particular over dt is going to be equal to plus 100 K e to the negative 10t. Right? Okay, so wonderful. So now we're going to plug this back into our differential equation, which, let's see, did I have one that had all the numbers in it? Yes, this one right here. So let's take this, copy that, put this in here, and then did I have the other stuff already written out? I did not. So, okay, so let's do the math for the IS over here. So R over LC is going to be 2 times 10 to the 9th times IS of t, and then plus 1 over C. Well, our 1 over C is 10 times 10 to the negative 6th, right? So 1 over that is going to be 10 to the 5th. And I bring this math up here because we showed how to derive this, and when we did the quiz, I think this value was actually 10 to the 6th, the one that was of the equation that was given to us. So we are actually going to stick to our guns here and think that this is 10 to the 5th and not 10 to the 6th. And this is dis of t over dt. Okay, so now we're going to plug and chug like we did in the previous one, except this one's going to be a little bit more involved. So let's go downward because we're going to need all the room we can get. So this is going to be 100 Ke negative 10t. This is going to be, so this is going to be plus 2 times 10 to the 4th times negative 10 K e to the negative 10t. And then this is going to be minus 10 to the 8th times K e to the negative 10t. All of that is equal to 2 times 10 to the 9th times 10e to the negative 10t plus, and this is what I was saying about running out of room, 10 to the 5th times the derivative of our source, which the derivative, our source was 10e to the negative 10t, right? So it's negative 100 e to the negative 10t. So negative 100 e to the negative 10t. Okay. And so now we're going to combine like terms. We have a lot of e to the negative 10t's, and as a matter of fact, every single thing in here has e to the negative 10t. So if we wanted to eliminate that in order to do our math, we can divide out. We can, essentially what I just did is divide everything by e to the negative 10t. So now you have 100k plus 2 times 10 to the 4th times negative 10k minus 10 to the 8th k is equal to 2 times 10 to the 9th times 10, and then plus negative 100 times 10 to the 5th. Okay? Okay, so I was going through this and I realized I made a mistake somewhere, and I figured out what it was. This is plus 10 to the 8th k. This needs to be a plus, this needs to be a plus, and I will show you where I made that error. I didn't want to have to go back and remake this whole video. So if we go back, this needs to be a plus, this needs to be a plus. This actually is still correct. I had plugged it into my calculator with the positive because I was following off of my computer where I had written it correctly. But when I subtracted here, this should have been negative VC. So I either should have divided through or I should have left the VC on this side and made this 0, 0, 0, 0. And I should have said plus VC, plus VC, plus VC. So this should have been plus there. This should have been plus there. And that didn't affect too much. Like I said, when I got my roots, I used my previous values from my computer, so I had done the roots correctly. But that is my bad, y'all. Trying to see if there's anywhere else that I messed it up. I don't think so. Everything else was based off of the actual differential equation and the guesses. So I do apologize for that. If you go through and run through this problem again, please make sure that you have a positive value here. That value was initially based off of this function right here, and I put the VC over to this side, but I didn't make it negative. So that was my apologies. This right here, that's where it should have changed. So negative VC is equal to all of that. So please keep track of your positives and negatives. This is a lot of math and a lot of algebra and such, so very easy to make mistakes. But I looked at this number after I punched it into my calculator, and I was like, there's no way. And so that makes sense, because it should be 100k plus 2 times 10 to the 4th plus 10 raised to the 8th. And then, oops, that's actually not correct. I need to include the negative 10 times the 2 times 10 to the 4th. So that number is correct, 998,001,00. And that is equal to this, which is 2 times 10 to the 9th times 10 plus negative 100 times 10 raised to the 5th. That is equal to 1.999 times 10 to the 10th. And let's see, does this match what I had? Yes, it is. Okay, and so then this is all times k. And so now we should be able to derive that all of that will come out to having a k value of about 200.3. Okay, and that is the correct answer. So I do apologize for that mistake. Thank you for following and working with me. But moving forward, we can now include the fact that the VC0 state particular of t is equal to 200.3. That's for your k value, so it's going to be times your e to the negative 10t. Okay? All right. And so now we can put together our VC0 state homogeneous plus VC0 state zero state particular, which is going to be a e to the negative 10 to the 4th t plus b t e to the negative 10 to the 4th t plus 200.3 e to the negative 10 t. Okay, and then our dvc of t over dt is going to be equal to, this is just going to be negative 10 to the 4th a e to the negative 10 to the 4th t plus, and then this is the same part we had earlier. I'm going to copy that because now I'm a little concerned. I don't want to be making further algebra mistakes. So let me copy that value from up here, wherever it was. Here we go, this right here. Well, let me just do this right here. Okay, and then the derivative of this is just a 10 up here. This is a different value, mind you. So this is going to be 2003, and it's going to be a minus now, e to the negative 10t. Okay, and so now let's plug in 0 into both of these. This is going to be equal to VC 0 state of t. So let's plug into 0 in both of these equations to find our a and b values. So VC 0 state of t of 0 plus is equal to, and what was our value of 0 plus for v? It was 0 is equal to a plus, this is going to go to 0 because of this t, right? Plus 0, and this is going to go, is just going to be 1, so plus 200.3. Okay, which means that our a is equal to negative 200.3. All right, and then using our dVC 0 state over dt, which is going to be equal to, if we go back up to here, we want our IC over C. So we're getting 10 amps. Well, it's this whole thing, but it's 10 amps because we're plugging in 0. So let me put in the 0 plus. Is going to be equal to 10 amps divided by your C, which is 10 microfarads, which is going to be equal to negative 10 to the 4th times negative 200.3 plus, this is still going to be going to 0. This function is not going to be going to 0 though, so this is going to be b, and then minus 2003. Okay, awesome. So now let's do this math. This is going to be 10 to the 6th, which is equal to 2,000, and then 997. So I guess that's 2,997,000 plus b. And then let's do 10 to the 6th minus that answer. We're going to get b is equal to negative 1,997,000. Okay. Okay, so that means that our VC 0 state total of t is equal to negative 200.3 e to the negative 10 to the 4th t minus 1,000,997 t e to the negative 10 to the 4th t plus 200, yeah, plus 200.3 e to the negative 10 t. Okay, and then let's combine our VC 0 input plus VC 0 state, and that's going to be equal to our VC total, which will be VC of t is equal to, the 0 input was this, and then the 0 state was this. Let's shrink it and stick it in there. Okay. So now let's combine like terms. So 400 minus 200.3. So we're going to have VC of t is equal to 199.7 e to the negative 10 to the 4th t. And then we're going to have 2 times 10 to the 6th minus 1,000,997. So this is going to be plus 999,003. T, e to the negative 10 to the fourth t. And then this is going to be plus 200.3 e to the negative 10 to the 10. E to the negative 10t. Okay, so this should be your particular solution to the, or sorry, not just the particular, that should be the solution to the entire equation. And then don't forget, actually, this is once again at u of t, because this is after we get to the time t is greater than 0. So, and actually, an easy way you can check this too, if we plug in Vc of 0, remember that our Vc of 0 plus was 400 volts, right? So we have 199.7. That's going to go to 1. This is going to go to 0 because of this t. This is going to go to 1 because of the t here. So plus 200.3 is equal to 400 volts. So this is obviously a slightly unknown, but believe it or not, we worked on this problem a lot, and we can confirm that this is the correct answer for the middle term. Took a little bit of extra work to get there, but thanks for sitting with me through these two problems. Again, I apologize for the negative answer error here with the VC. Hopefully y'all were able to figure it out. But thanks for watching. I hope this helped make a lot of sense. The concept of looking for, just to go over once again, what you want to do here is, you want to set up your t as 0 minus to find your initial conditions. Then you want to go t0 plus so that you can derive your equation. Then still at t0 plus, you're going to do your 0 input, and then at t0 plus, you're going to do your 0 state. And remember not to plug in your initial conditions for your 0 state until you've already done this thing right here, until you've already done both your homogeneous and your particular solutions. All right, I hope that helped everybody.
All right, Mr. White, be cooking. So